Okay, so today we're going to talk about generating functions. And in general, we usually refer to them as moment generating functions. So first off, I'm going to define the expectation of e to the tx as my function of study. And we're going to begin by noting that this is a fairly simple form. But one might ask yourself, why would in the world would you bother to look at something like that? Well, it turns out that, first off, it's kind of cool that this can be calculated. And what's really interesting to note is that the x varies over the entire sample space. What's left is going to be some function of t. And so we're going to call this m of t and define this as our moment generating function. And we're going to ask what it does for us. First, we're going to note that in general it does very little, but it does contain information. So let's begin with for example, a discrete function that takes on a set of values. Let's say we have x is equal to some a1, a2, a3, a4, let's do up to ak, a set of values. And associated with them is the probability of each one of these. So we have f of a1, f of a2, etc. I don't even need these to be sequential, I just want them to be discrete. So what does this say? Well, it says that the expectation then of e to the tx would be a sum over this a1, a2 up to ak, e to the tx, f of x, and basically you'd get e to the a1x, f of a1, plus e to the a2x, f of a2, all the way e to the ak, f of ak. It looks very, very boring. Let's take the discrete uniform function. So let's say f of x equals 1/6 on x equals 1, 2, 3, 4, 5, 6. The roll of a die. What does this m of t look like? Well, this m of t then would be each one of these is 1/6, so I'll factor it out. And we would get, oops, that was a t for each one of these. Apologies. It would be e to the 1t, e to the 2t, e to the 3t, e to the 4t, e to the 5t, e to the 6t. And that's what the m of t would look like. Now, the m of t contains all of the information about the function itself. What's really neat about the m of t is the algebraic properties that it has. All right, so what exactly algebraic properties do we think we're going to find with this m of t? Well, let's begin with a new distribution that we haven't talked about too much. This distribution is discrete. I'm going to use 1/2 to the x as its power. And I'm going to let x vary 1, 2, 3 to infinity. Now, before I do much with this one, this is a geometric series, basically. So one of the things I should check is, well, it's very clear that f of x is greater than 0. But is it clear that the sum of 1/2 to the x equals 1 to infinity, adds up to what it should be? Well, that's 1/2 plus 1/4 plus 1/8. Well, this is 1 plus 1/2 plus 1/4 minus 1. So I added 1 and subtracted 1. This is the well-known geometric series, which is 1, so it works well. This is a very nice geometric series, and I've got to update my battery. Okay, so this is a well-known geometric series. Let's calculate the moment generating function for this series. So, definition of the moment generating function, m of t, is the expectation of e to the tx which would be the sum over x equals 1 to infinity of that e to the tx f of x. But our f of x that we were just looking at is e to the tx 1/2 to the x equals 1 to infinity. Now, how should I add this thing up? Well, the answer is it's not really hard to add up. X is the variable that's changing, so I'm just going to do a little algebra on the inside. Observe that powers distribute, powers go to the power. And so this is a geometric series, except the head has been cut off. This is an a to the x. And if I started at 0, and then subtract 1, why, we know exactly what this series is going to be. Geometric series, subtract 1. I leave it to you guys when a equals e to the t over 2, that you get e to the t over 2, 1 minus e to the t over 2. Now, it does require, though, that this geometric series have a very specific allowable value. And so, this is over 2, like down there. It does require us that the a has the right value, and this is, in order for this to converge, you have to have t less than log 2. So there is a very specific value that needs to happen in order for this thing to converge. So we constructed a moment-generating function. Now, this moment-generating function looks wild, but I want to demonstrate with this moment-generating function, I can rebuild the PDF from it. Algebraically, it's embedded in there. So how in the world can it be algebraically embedded in there? Well, first off, I'm going to do some algebra that you may remember from long ago, called the geometric series. Wasn't that our start here? Isn't this that's a geometric series, right? Well, let me write this as e to the t over 2 times 1 over 1 minus an e to the t over 2. And now let e to the t over 2 go into here. And so we get e to the t over 2 in front times, and putting e to the t over here 2, I'll get 1 plus e to the t over 2 plus e to the 2t over 2 squared plus e to the 3t over 2 cubed. And then when I multiply this back out, I'll get e to the t times 1/2 plus e to the 2t squared plus e to the 3t over 3 cubed. Why, lo and behold, I get e to the 1t f of 1. F of 1 is 1/2. Plus e to the 2t times f of 2, where f of 2 is 1/4. Embedded in that geometric series is f of x equals 1 over 2 to the x. It is sitting inside of there for each and every term. So inside of this small algebraic expression is the entire geometric series and its probability function. Now, that's not just the only algebra one can find in the moment-generating function. Next thing I'm going to do is I'm going to take this moment-generating function's definition and I'm going to plug in 0. So if that's 0, I just get e to the sum of the function. So m of 0 is 1. Kind of a boring fact. Nothing crazy cool about that. Now I'm going to take the derivative of m of t. So t is the variable, x is our constant over this sum. So this becomes a sum. E to the tx is derivative, and t is the variable is x. E to the tx, f of x, x and s. And now when I plug in 0 into this goes away and I get the sum of x, f of x, x and s lo and behold, that's mu. So inside of the moment generating function is the expectation of the PMF built right into calculus and an evaluation. Now, the curious thing is when we do m double prime, we take another derivative, we get x squared in the front. And when we plug in 0, m prime, double prime of 0 is the sum of x squared f of x, which is the second moment, the expectation of x squared. And this continues, and hence the name, the moment generating function. So if you want to take the kth derivative of the moment generating function and then evaluate it at 0, why, lo and behold, you're going to get the expectation of the kth moment. Now, this is powerful. Why is it powerful? Because it says that a single function with the combination of calculus and evaluation contains things that we're interested in, the standard deviation, the moments, the mean. It algebraically binds all of the information together. So let's do one of these calculations. Let's do the binomial function, binomial PMF. Now it's time to start noticing that we just saw a PMF called the geometric series that had an infinite but discrete support. This one has a finite, but it starts at 0. You're starting to see some patterns where you can actually just look at the domain of your PMF and take a good guess at what type of function you might be working with. So now we're going to calculate the moment generating function, expectation of e to the tx versus the sum over x and s of e to the tx, f of x. Now our f of x here is a very well-known function, but when you put the e to the tx in front of it, it doesn't look as simple. Or does it? Well, why don't we see if we can do the trick that we did before, where if we have a power of x and a power of x, who cares that it's with an e? Let's combine those two pieces. So let's leave the sum alone. Let's take the e to the tx and p to the x and put them together. So common of e to the t, p to the x, q to the n minus x. Now, do we know that? The answer is yes, we do. That's the full binomial row in a binomial expansion of a plus b to the n, where a happens to be e to the tp and b happens to be this q, and so we get the full sum of the binomial row, which is q plus p e to the t to the n. And we have now, and we can replace q with 1 minus p if we like, and that's commonly done. We now have the moment generating function for the binomial distribution. What's neat about this, it is not hard to do calculus. In fact, it's pretty straightforward. Take the derivative. T's inside, power is there, means we pop the power in front, reduce the power 1, leave the inside alone, and then multiply that times the derivative of the inside. And if we choose to evaluate it at 0, we're going to get n. This will be 1. Oh my goodness, we get np. I leave it to you to do m double prime of t and then evaluate it at t equals 0 and discover that you also have a formula for the standard deviation of the binomial series. Now, what's really neat about these moment generating functions is they are very powerful in what they contain. they make calculating averages, standard deviations, much, much simpler. Okay, time to introduce another PMF. So this PMF is related directly to binomial. So the binomial PMF is a count. And the count can range from 0 up to some value n, and associated with it is a characteristic 1, and the probability of achieving characteristic 1 or a success is p, and therefore not characteristic 1 is 1 minus p. Now, one would say that it seems very reasonable that we would like to count a little bit differently. In other words, we'd like to wait for something in the count. So what happens if we're doing a repeated Bernoulli and we're waiting for, let's say, the 12th heads to happen? So you're doing a flipping of a coin. Don't know the probability, doesn't matter. It could be an unfair coin, it could be a weighted coin, who knows. But we're flipping, and we're waiting for the 12th occurrence. Well, first off, the probability of it happening before 12 is impossible. It's 0. You can't get 12 heads if you only flipped a coin 10 times. So obviously, the domain of whatever function we do here when we're waiting is going to start at this count and then go up by 1. So it is a very different type of domain. And since you're waiting for 12 heads, you really don't know how long it might take to get. I mean, you might have a very bad coin that has like 1 in a billion chance of getting a head. This basically goes on forever. You must accommodate bad coins or just bad luck that you're flipping. Now, we're going to use this one. I'm going to give you the formula, and it looks like this. Now, let's just interpret this once. First off, you have to have certain successes or non-successes. So right here, you've had r minus 1 occurrences, and you've had x non-occurrences, but we want to have one more occurrence of the success. So this counts the ways you reach one short of r successes. And then, when you add one more p to this, you get a distribution which starts at r, goes to r plus 1 forever, and you are waiting for the rth. And I say the word success, but that's just the occurrence associated with characteristic 1 in the repeated Bernoulli that we're looking at. This is called the negative binomial. And in reality, the negative binomial looks kind of complicated, but it occurs quite frequently. In fact, think about those families that have 8 daughters that you've heard about. You think they were experimenting with maybe waiting to see when they got their first son, and it just kept on going and going? The negative binomial is a count that is a waiting count. The probability of when a specific thing is going to happen for you. All right. Well, since we're doing all these neat distributions, we should point out that that negative binomial distribution, if that we set it equal to r equals 1, it looks like this. That looks very familiar. That looks like we've put this in a tree before. P, Q, P, Q, P, Q. I want to affiliate with this the reverse concept of success and failure. How about P is associated with a failed rocket launch? And 1 minus P, which is Q, is a success. What does this mean? Well, this means that if you fail, it's over. But if you succeed, you can go again. If you succeed, you can go again. But when you fail, it terminates. So you're really only interested in when it finally fails. You get one failure and many successes. This particular PMF is called the geometric PMF. The other one, where we had 1/2 to the x, is not called the geometric distribution. This one is called the geometric distribution. This is an absolutely great distribution to work with. It is simply astounding. Well, I'm going to stop with that one and put this video up. And looks like we're going to have 2 sections for moments here, so I'll have to do another one tomorrow.